Dear participants, we are honored with the presence of our guest speakers, Professor Alan Driffens. He is currently professor at International School of Paper and Print Media and Biomaterials at very renowned institute, Grenoble Institute of Technology, France. It's very near to a city, Lyon, and the Lyon is very close to my heart and Professor Uni's heart. I visited Lyon in almost 12 years before, 2012, and I have seen the quality of science and education over there. He obtained a PhD in electronics from National Institute of Applied Science at Toulouse and Masters in Chemical Engineering from École Polytechnique de Montréal. I think it's in Canada. And in solid state physics from Paul Sébastien University, Toulouse. So he has a wide background. He's an expert on polysaccharides, nanofibers, and nanocrystals, cellulose, chitosan, starch, etc., and on processing and characterizations of nanocomposite based on renewable resources and on valorations of biomass. He's having wide collaborative projects, and recently he's working with Chinese company which could generate a nanocellulose. He has been recognized as highly cited researcher and highlights the top 0.1% of most cited researcher in the world. And it's in consecutive years. So since last 10 years in France, in world, in Europe, he's that among not only the top 1%, he's top 0.1%. As per the ranked, he's ranked 208 worldwide and second in France as per the research.com 2020-24 ranking database of best scientists in material science. He has published more than 350 international journals, articles, review, and he has more than 77,000 citations. Quite impressive, 77,000 plus citations. And his H index is 141. So, you know the H index means that many paper has cited that many times minimum. So he has at least 141 paper which have cited it at least 141 times. So it's as per the Google Scholar in many leading journals. Many of his paper was selected as the ESI top 1% highly cited paper or 0.1% hot paper, and highly highlighted as a key scientific article contributing to the excellence in environmental research. His research interests include polysaccharides, nanomaterials, cellulose, chitosan, and starch, processing and characterizations of nanocomposite based on renewable resources, and valorations of biomass. So, and he has a lot more achievement in his own. So those are very difficult to read, and if I have to read all, it will be probably a session. So I will not take his more time. So with these few words, I welcome Professor Allen. And moreover, he is a very good person. In last 2 days and since last 1 month, I am in touch with him. I am honored to have a person like Alan in our department, in our institute, in our country. So with these few words, I request Professor Allen to take the session. Please, floor is yours.
Good morning again. So it seems that in India, science attracts mainly women. I will start with a short introduction or general introduction on biocomposites. So in some sense, so it was also done by Professor Unikrishnan. We have the same source. Yes. So this is a definition of a composite, but you already know from the previous presentation. So it's a material that consists of two or more identifiable constituents. So this is important. For example, we can consider polymer blends. In the case of polymer blends, we can have some miscibility at the interface. And so this is not the case for composites. So generally, this composite consists of a fiber that has a high modulus to provide some reinforcement, and it is embedded in a comparatively lower modulus matrix. So you know that the modulus of polymers, so it depends on the temperature, of course, but it briefly ranges from 1 gigapascal in the glassy state at low temperature, and 1 megapascal, for example, for a rubber, for a rubbery material. So the objective is to combine a fiber that has a high strength, high stiffness, low density, if possible, with a polymer matrix that has good shear properties and also low density. And so the composite result, or the properties of the composite result from these different properties: high strength, high stiffness, good shear properties, and low density. So the function of the matrix and of the reinforcement have been highlighted just previously. The matrix is necessary to hold the reinforcement in place and shape the product, to deform and distribute the stress to the reinforcement when applying a load, because of course the load is applied to the matrix, and it is necessary to transfer this stress to the fibers that can support higher loads, and to provide a chemical protection. So for the reinforcement, so of course it provides the mechanical properties. So we can have different orientation. It can be adjusted depending on the application of the material. So this has been outlined also previously. So composite can be obtained or can be qualified as particle reinforced or filled composites. So in this case, so when using a filler, the objective is slightly different. Using a filler means that the objective is to decrease the price of the final material, meaning that it's necessary to use low-cost particles. This is the first objective, but of course, all other properties, like the mechanical properties, are impacted by the presence of this filler. We can have fiber reinforced composite or structural composite like laminate and sandwich. It has been also highlighted previously. And for fiber reinforced, continuous or discontinuous fibers that can be aligned or randomly oriented. So the matrix can be a thermoset polymer, so a 3D polymer network, or a thermoplastic polymer. And the reinforcement, so can be from synthetic, plant, mineral, or animal origin. So the first question is why using the reinforcement as fibers? And we can find this also in nature. For example, in natural fibers, cellulose occur as long fibrils that we will see previously. We can consider any kind of material. So this material has some defects, of course. We can call X the number of internal defects, Y the number of surface defects. And then when dividing this material into fibers, so n times on each face, so meaning that we have n square fibers, of course the number of surface defects, increases. We have the same number of internal defects, but a higher number of surface defects. Now, when determining the number of intact fibers, so the fibers where you have no defect, it's n squared, the total number of fibers, minus the number of fibers where we have defects, internal or surface defects. And you can see from this equation that by increasing n, we can increase the number of intact fibers. And this is the objective, so it means that it's necessary to use as thin as possible fibers. But of course, it's necessary to have a binder to link these fibers. So now we are dealing about the bio-based or green materials. So you know that there is an increasing demand for products which are made from renewable and sustainable base resources, which are not dependent on the petroleum, which are sometimes called green materials. But of course, for this, it's necessary to have a material which has a low cost or not too high, at least to compete with other materials. And a good source of material is polysaccharide. Polysaccharide include cellulose, starch, chitin, and some other. I just say this one because cellulose is the most abundant polymer on Earth. And it is free. It is provided by nature. And it is renewable. So it means that it's a good source, at least from an economical point of view, to prepare or to obtain new materials. So some definition. A biocomposite is a composite material which is made from natural fibers and petroleum-based non-biodegradable polymers, so polyethylene, polypropylene, epoxies, etc. It can be also a biopolymer, of course, and even a biodegradable polymer like polylactic acid or polyhydroxyalkanoates. When this material is made from a biopolymer and synthetic fibers, and when the matrix is bio-based, so it's also a biocomposite. You can see these two ways here, which are called partly eco-friendly materials. But of course, we can use a mixture of bio-based fibers and bio-based polymer as the matrix. And this kind of material is, of course, more eco-friendly and sometimes called a green biocomposite. We can also think, of course, about hybrid biocomposites consisting of a blend of fibers, glass fibers and natural fibers, or a blend of a polymer blend mixing a biopolymer and synthetic polymer. So some history about composites. So this is very old. Mud brick, which is a mixture of clay, plant fibers, usually straw was used, and water. So this is a composite material because there is a reinforcement and a matrix. And so this is very old and can be almost everywhere in the world. Some other important step for biocomposites. So in 1908, cellulose fiber phenolic resin were developed for the industrial production of panels and tubes for the electronic industry. Also, during the Second World War, there was a shortage of aluminium in UK, in England, and so composites made of flax fibers impregnated with thermoset phenolic resin were used for some part of Spitfires. So I'm sorry, I made some noise with my beard. Another example in the car industry with Henry Ford, he developed some prototype consisting of hemp fiber and soybean resin to prepare some parts, at least of the car. And according to him, it's very strong. I'm not sure it is true, this photo, but anyway. His argument was that the most environmentally friendly thing that you can do for a car that burns gasoline is to make lighter bodies. And so this is true, and this is very important for any kind of transportation. This is another example. I don't know if you know this car. It's a Trabant. It was developed in East Germany. In this car, part of the internal part was made from natural fiber, it was cotton in this case, and polyester matrix. And so now there are more and more examples of the use of natural fibers composites, and this is of course due to some advantage of natural fibers. I report here the most important advantage. Of course, there are some drawbacks also. The first advantage is the density, which is low. Typically, for natural fibers, it's between 1.3 to 1.5 gram per cubic centimeter. If you compare to glass fiber, which are broadly used for composite manufacturing, the density of glass is 2.5 gram per cubic centimeter. So it's a lighter material. It's a low-cost material because in some case, byproduct from agricultural industry can be used. So you mentioned banana fibers. So this is one example. So it's low-cost material. The mechanical properties in terms of strength and modulus are quite high. So I mentioned here high specific strength and modulus. In fact, a specific property is a ratio of one property that can be the strength or the modulus divided by the density of the matter. So renewability, biodegradability, these materials are available in a variety of forms throughout the world, and so depending on the location, different natural fibers can be used. For example, in France, it's mainly flax and hemp. I don't know exactly for India, maybe banana. But so anyway, you can adapt depending on the local resource. These fibers are flexible, which is important because during composite processing, so different equipment can be used, can be, for example, extrusion. During extrusion, high shear rates are applied to the material. And when using glass fiber, of course, the result is a decrease in the length of the fiber, which is not the case with natural fibers because they are flexible. So these fibers are also non-abrasive for processing equipment. They are non-toxic, easy to handle, high ability for surface modification. This is important because cellulose has a high density of hydroxyl groups. And of course, the chemistry, I'm not chemist, but the chemistry of alcohol is very broad, and you can adjust the surface properties of the fibers. Possibility to generate energy without residue after burning at the end of their life cycle. So you know that a big part of polymers are recycled by burning to recover energy. And of course, if the material contains 30% glass fibers, this is not burned. So it is a residue, which is not the case with natural fibers. And so last, economic development opportunity for non-food food farm product in rural areas. So of course there are some drawbacks. The first one is linked to the hydrophilic character of natural fibers, and mainly cellulose. It results in poor adhesion and poor dispersion in a polymer matrix that is in general non-polar. Like when you try to mix oil and water, there is a phase separation. High moisture absorption can be also a drawback. Limited thermal stability. In fact, cellulose starts to degrade around 200 degrees Celsius. So it means that you cannot use this composite at high temperature, and you have to take care about the processing conditions. This is not really an obstacle or drawback, because most of the polymeric matrix can be processed at lower temperature, typically polystyrene, polyethylene, polypropylene, and so on, which is not the case for polyamide. And another drawback is variable properties. We'll see later that the properties of natural fibers, so depends, of course, on the source of natural fibers, but also on the climatic condition, the nature of the soil, the age of the plant, and so on. So it means that you have variable properties, but it's a natural product. Usually, in biocomposite industries, a mixture or blend of fibers that have been harvested during the last 5 years are used just to homogenize the properties. So these natural fibers can be from plant, animal, or mineral origin. So you have different examples here that I will not detail. But of course, plant fibers or plant natural fibers are mainly used. These fibers can be extracted from the seed or the fruit, which is the case for cotton or coir, from the bast, which is the case for flax, and jute, rami, kenaf. I think jute is probably a good source in India for natural fibers. Leaf, like for pineapples, sisal, abaca, henequen. Straw fibers, wheat, maize, barley, oat, rice, grass, and reeds, which is the case for bamboo and bagasse, or wood fibers, of course, which are broadly available also, can be soft and hardwood, or we can also use recycled fibers. So this fiber comes from what is called the biomass. So it is produced for free just because of the photosynthesis, because of the sunlight. So it's necessary, of course, to use water for these plants. And this combination, using carbon dioxide from the atmosphere, lead to the formation of carbohydrate. And you can see the equation here, and you can see that the byproduct is oxygen. So it means that, of course, this biomass or these plants are very important for us to live on Earth. There is also a respiration mechanism that releases water, carbon dioxide, and oxygen. So now regarding the composition of these natural fibers, these natural fibers are composite materials. So it means that they consist of different materials, and each material provides some properties. The most important one, which represents about 50% of the natural fiber, is cellulose. Cellulose provides the mechanical properties to natural fibers, or to plants, to trees, and so on. So you know that cellulose is hydrophilic, and usually the plants are outside, of course. So it's necessary to protect the cellulosic material from moisture. And for this, there is a matrix which is composed from another polymer, which is called lignin, which is an hydrophobic polymer that protects cellulose fibers from moisture. And of course, because we are considering a hydrophilic and an hydrophobic material, it's necessary to compatibilize this material. And this is the role of another component, which is called hemicellulose. And we can find also some other materials like waxes, pectin, and so on. But these are the three main components of natural fibers, which are represented here. Cellulose, called by hemicellulose, and the matrix is lignin. So this natural fiber, this is the structure of the cell wall, consists of tubes. And these tubes consist of what is called primary wall, in which you can see a random orientation of cellulose in the form of fibrils. So remember, it's always important to have thin fibers or thin fibrils to have mechanical properties. And then we found three other walls, which are called secondary walls, S1, S2, S3. The thicker one is S2. And you can see that in these walls, or in these layers, there is a given orientation of the cellulose fibrils. So, we have three main components. Cellulose. You can see the chemical structure of cellulose here. So it's a linear macromolecule, which is composed by this monomer unite. The DP is very high, so it's generally around 10,000, but it is difficult to determine because the first step to determine the molecular weight or the degree of polymerization of cellulose is to extract cellulose from natural fiber. And this extraction process generally degrades the polymer, so it means that it decreases the molecular weight. You can see also on these molecules there are two different ends. What is called a non-reducing end and a reducing end that we'll discuss later. The production is very high, so this is an estimation. This is produced every year and it is regenerated because it's a renewable material. So the most abundant polymer on Earth. To give you an idea, a tree on average produces about 10 grams of cellulose every day. Probably more in Kerala, because of the weather. Cellulose is a semi-crystalline polymer. It means that we have some amorphous domains and some crystalline domains. And we have what is called a polymorphism of cellulose, meaning that we have different crystalline states. Native cellulose is called cellulose 1. It can be cellulose 1 alpha or cellulose 1 beta. Usually we have a mixture of these two different elements. So you have the definition here of 1 alpha and 1 beta. So it's a different unite cell for the crystalline domains. So generally in alga we found mainly 1 alpha cellulose, and in trees, for example, it's mostly 1 beta. It's possible to change this crystalline state to another one, which is called cellulose 2. And this can be done by two processes that I will detail in the next slide, mercerization or regeneration. And this transition from cellulose 1 to cellulose 2 is irreversible, meaning that cellulose 2 is the most stable state or crystalline state of cellulose. And then by a treatment with ammonia, it's possible to convert cellulose 2 to cellulose 3, and then by a thermal treatment to cellulose 4, which is another crystalline form. So mercerization, which induces the transition from cellulose 1 to cellulose 2, is an alkaline treatment. And regeneration is a process that involves dissolution and precipitation. There are not so much solvents for polymer, for cellulose, sorry, but there are some. So this is some description about the cellulose 2. So I mentioned previously that the transition 1 to 2 is irreversible. And what is important in terms of difference between these two crystalline forms is the orientation of the macromolecule. So remember that cellulose chains have a reducing and a non-reducing end. Cellulose 1 has a parallel chain orientation, meaning that all reducing ends are on the same side in the cellulose fiber. Cellulose 2 has an anti-parallel organization. And so this results from this different treatment. So cellulose 2 can be used. It has some practical or industrial application, like for example for films, in the form of cellophane, for textile fibers, so rayon, lyocell, membrane for dialysis, filtration, paper for packaging, and also for cellulose derivatives, so you know cellulose ether, cellulose ester, and so on. And it is used also by the pharmaceutical industry. So now hemicellulose, which is another component of natural fiber. So it's a polysaccharide which is composed by a combination of 5 and 6 ring carbon sugar. The degree of polymerization is much lower compared to cellulose. So it's from 50 to 300. This macromolecule is branched. And you know, when branching is present, usually it limits the possibility of crystallization of the macromolecule, meaning that hemicellulose is non-crystalline or amorphous. So it forms a supportive matrix for cellulose microfibrils. It's a very hydrophilic polymer, which is soluble in alkali and can be easily hydrolyzed in acid. So there are different forms of cellulose depending on the source of natural fibers. And the third important component is lignin. This is a compound that gives the stiffness or the rigidity to the plants because it links or it brings together the cellulose fibrils. So it's a complex three-dimensional copolymer of aliphatic and aromatic constituents, as you can see here. The molecular weight is very high. The carbon content is also high, and the hydrogen content is low because of this aromatic structure. So it's an amorphous polymer. It is hydrophobic, and the TG, the glass transition temperature, is around 130 degrees. So it mainly consists of these three components. So lignin is made from these three chemical groups. So depending on the source of natural fibers, the chemical composition can vary. You have here some example of natural fibers with the cellulose content, hemicellulose content, lignin, and some other constituents. We can see, for example, for coir, the cellulose content is very low, but the lignin content is high. On the opposite, for example, in the case of flax or hemp, the cellulose content is important. And we'll see that this chemical composition, of course, impacts the structural properties of the natural fibers. I also previously mentioned that this composition can vary depending on the climatic conditions, the age of the plant, the digestion process, and some other elements that, so it's a natural product. So I come again on this representation of the natural fibers. So I didn't mention previously that you can see that there is a hole in the middle of the fiber, which is called lumen. And this lumen is necessary to transport water in the plants. So in most plant fibers, the cellulose fibril or microfibril are oriented, at least in the secondary walls, at an angle to the normal fiber axis, and this angle is called the microfibrillar angle. And we'll see later the impact of this microfibrillar angle. So you have here the typical dimension of natural fibers. When considering a single, which are also called elementary plant fibers, or single cell, you can see that the length is around 150 micron, the diameter range from 10 to 50 micron, which is similar to what is found, for example, for glass fibers or carbon fibers also. But usually in biocomposite, technical plant fibers are used. So it consists of a fiber bundle. So of course the dimensions are much higher. The length can be up to 1 meter. And typically the diameter range from 50 to 100 micron. You can see here this technical fiber that consists in the association of many elementary fibers. So you understand that cellulose is probably the most important component, at least for biocomposite. Of course, hemicellulose or lignin can find application in other sectors. And the reason for this is that cellulose provides the mechanical properties to plant fibers. So it means that we need this element to reinforce polymeric matrices. You have here two graphs in which you have the evolution of the strength of the fibers as a function of cellulose content and as a function of the spiral angle. So the spiral angle is this microfibrillar angle. So it's exactly the same thing. And you can see, so for different natural fibers, and you can see that there is a kind of correlation. When increasing the cellulose content, we observe an increase in the strength of the fiber, and when increasing the spiral angle, we observe a decrease in the strength of the material. So it means that to have efficient natural fibers, it's necessary to have a high cellulose content and a low microfibrillar angle. So some equations have been proposed to determine the strength of the fiber and the elongation at break as a function of theta, which is this microfibrillar angle, and W, that represents the cellulose content. So this is for some natural fibers, some physical properties like the density, as mentioned previously, so it's around 1.4 to 1.5 gram per cubic centimeter, the Young's modulus, the stiffness, the tensile strength, the elongation at break, and the microfibrillar angle. And these values are compared to the values obtained from synthetic fibers like glass fibers, aramid or Kevlar fibers, and carbon fibers. In terms of density, you can see that the density of natural fiber is similar to aramid and carbon, and much lower than for glass. In terms of Young's modulus, so it's difficult because, of course, there is a broad range of values, but except carbon fibers, the modulus is not so far from the modulus of other fibers. And so elongation at break is more or less similar, so it depends. In the case of quartz, you can see that the microfibrillar angle is higher, meaning that the strength is low, but the elongation at break is higher. So the first step is the extraction of fibers. It's called the separation in the processing, which is also called rating. Rating consists in the degradation of the pectic polysaccharide by biological activity of microorganisms, bacteria and fungi, which are from the environment. So sometimes a mechanical treatment is added to help the separation of the fiber bundles. And so you can see here this mechanical separation process. And of course, this extraction process also impacts the mechanical properties and other properties of natural fibers. So these are some, let's say, different types of rating process that can be used. It can be a biological process that can be natural. So it just consists in resting the fibers in the land, which is called the dew or fill rating. Artificial biological rating that use hot water in order to improve the speed of the process, can be mechanical, which are also called green rating, physical, ultrasound rating, or steam explosion. So steam explosion consists in inserting the natural fiber in a container containing water in which the pressure is increased and the temperature is increased. And the pressure is suddenly released in order to explode the natural fibers. Or it can be a chemical rating process. You can see here the impact of this rating process on the aspect of the natural fibers. This is for flax fibers, so you have to remember, yes, it's a different orientation of the fiber. So non-rate fibers, you can see that we have some agglomerate or bundles of fibers, and you can see also on the surface of the fibers some roughness. This roughness comes from the presence of non-cellulosic material like lignin and hemicellulose. And after rating, so in this case water rating for 7 to 2 hours, we can see that we have separate more or less the fibers, not individually, but at least the bundles are not so big. And you can see that the surface of the fibers is smoother because of the removal of non-cellulosic materials. So sodium hydroxide can be also used to remove this non-cellulosic material. So this is an example. So this is for kenaf fibers of the effect of this alkaline treatment. So it fibrillates the fiber bundles into smaller fibers. So it separates the fibers. So now these natural fibers can be used to process biocomposite using a polymeric matrix. So I mentioned previously that one drawback of natural fiber or cellulosic fibers is their polar nature. They are highly hydrophilic. It results in a poor resistance to moisture and difficult miscibility with polymer matrix, which are usually non-polar. So these are the typical polymers that are used in association with natural fibers to prepare composites, or biocomposite. So for thermoset polymer, polyester, epoxy, or phenolic resin, and in the case of thermoplastic polymers, so classical thermoplastic like polyethylene, polystyrene, and polypropylene. And of course, the chemical structure of these polymers differ, and the affinity towards the natural fibers can also be impacted. So usually a surface modification treatment is used. There are two options. The first consists in changing the hydrophilicity or hydrophobicity of the matrix. So to turn the matrix from hydrophobic to hydrophilic, to compatibilize with hydrophilic fibers. It is not the best option because finally we have a material which is sensitive to moisture. So meaning that generally the treatment is performed on natural fibers. And so it consists in turning the hydrophilic natural fiber to hydrophobic. So I mentioned previously that one important parameter to have an efficient reinforcing effect is the stress transfer at the interface. So the stress or the load is applied to the matrix, which is the outer part of the material. It is transferred to the fiber that can support higher load. But for this, of course, it's necessary to have a good degree of adhesion between the fiber and the matrix. So this strong adhesion is necessary, and to improve the mechanical properties of the composite, a coating is applied. Generally, so there are different options, but generally it consists of coupling agent or compatibilizing agent that introduce chemical bonds between the fiber and the matrix. It can be also physical bonds. So this coupling agent facilitates the optimum stress transfer at the interface, and this compatibilizing agent needs to have two functions. The first one, that will be able to react with the OH groups from cellulose, and the second one that will react with the functional groups from the matrix. So there are mainly two families of compatibilizing agents which are used, which are called silane and isocyanate. So you can see here the process of compatibilization when using a silane agent. So it is this kind of molecule that reacts first with water, and then there is a self-condensation process, and then hydrogen bonding that promote interaction or adsorption to the natural fibers, and then by increasing the temperature, a chemical grafting. So we have this chemical grafting, and you can see that the outer part of the fiber is now more hydrophobic. So the same thing can be performed using isocyanate. So this kind of chemical reaction can be called uratinization, carbonylation, and carbamation, it seems. I'm not chemist, but it can be used. And so the objective is to have some interactions between this isocyanate group and the OH group from the surface of the fibers. So it's possible to use aliphatic and aromatic mono isocyanate, but also diisocyanate. You have some examples here. And these are the different scenarios when using a monoisocyanate. So it means that we have only one NCO group on one end of the molecule that react with the OH group from the surface. And so, of course, we have here an aliphatic chain, meaning that the fiber is now more hydrophobic. We can use also diisocyanate, and here there are different scenarios. So we can have a reaction of one OCN group with the surface of the fiber, and the free isocyanate group is free to react with some functional groups from the matrix. Or we can have different reaction paths, but that result in the same final product. So this is very similar, the isocyanate grafting or treatment with methyl dimethyl isocyanate in this case. So I will not, it's similar to what we have seen previously, except that in this case, you can see that the diisocyanate is used. So we can also use chemical treatment. And I have to say that I prefer this physical treatment, first because I'm not chemist, and secondly because chemistry involves an additional step that can take time, so it means that it's costly. Treatment can be performed with copolymers. Probably know that a copolymer is a polymer that results from at least two monomer unites, and we can have different arrangement of this monomer unites along the macromolecules. So this is a homopolymer with a single monomer unite. Copolymers that can be alternating. You can see that there is an alternance between one monomer and the other. Random or statistical. There is no regular arrangement of the macromolecule. Or we can have a block copolymer with one side of the macromolecule that consists of one monomer and the other side of the other monomer. This is a diblock copolymer, so it's possible also to use tri-block copolymers and so on. And usually this kind of block copolymer is used for compatibilization between the natural fiber and the polymer matrix. One good example is copolymers containing maleic anhydride, which is hydrophilic and can react with the OH group from the surface of cellulose. So the other block can be polypropylene, it can be PLA, it can be polyethylene, so depending, of course, on the nature of the matrix. It is generally a copolymer, or it can be a random polymer also, that contain only few percent of maleic anhydride unite. And you have here the shell, so this group, maleic anhydride group, is attracted by the OH group on the surface of natural fibers. It can be chemically graphed or physically adsorbed, and then the rest of the macromolecule or the copolymer consists, for example, in polypropylene, and of course, there is a good compatibility with the polypropylene matrix. So, as a conclusion, a composite material consists of two or more identifiable constituents. Biocomposite is a term which is used for composite materials that are produced entirely or to a large extent from biomass, so it can be natural fibers with a synthetic matrix, or it can be a biopolymer, that is used as a matrix and synthetic fibers. So using natural fibers has many advantages, we've seen previously, but also few disadvantages. The structural features and chemical composition of these natural fibers depend, of course, on the source, or the botanic source of these natural fibers, but also the climatic condition, the age, and the digestion process. All these natural fibers are composite material. They are designed by nature, and we'll see later that it is really optimized in terms of mechanical properties. And in this natural fiber, on this composite material, cellulose acts as the structural material, so it provides the mechanical properties. The strength of the fiber increases when the cellulose content increases and when the microfibrillar angle decreases. And as we mentioned later, fiber surface modification is key for improving the compatibility of these natural fibers with matrix, polymer matrix, which is usually hydrophobic. So of course we can find some hydrophilic polymers like polyamides, but there is a difficulty with polyamides. The melting point is very high. So it means that it cannot blend at high temperature with natural fibers. But of course, we can think about other natural matrix, like starch, for example, that can be used. And because this matrix is hydrophilic, so it's not necessary usually to compatibilize the fiber with the matrix. So thank you very much. Do you have any question?
The session is open for questions, queries.
So there is, I'm quite new to this field, so I'm a little confused on how the composition of, how the amount of cellulose and hemicellulose present in the entire biocomposite alters its properties. Does it affect the properties?
How it impacts the properties, you mean, of the composite?
Yeah.
Um, it's mainly because, so when the cellulose content is higher, we've seen that the strength or the stiffness of the fiber is higher. So it means that when we have natural fibers with a lower cellulose content, we cannot expect so good mechanical properties. But sometimes it's not a problem. Sometimes it's not a problem. For example, quartz can be used. And so in some place, for example, in Kerala, this is a very abundant resources. In fact, I have to say that when using natural fibers in general, when we keep the same mechanical properties or the same properties as the matrix, it's not so bad. We can expect some increase in mechanical properties, of course. This is the ideal case. But at least if there is no decrease in the mechanical properties, it's not so bad. It's not so bad because for example, you can use polyethylene as the matrix. And if you can substitute maybe 30% of this polyethylene by natural fibers, so the material is greener and you keep the same mechanical properties. Okay? But of course, the composition has an impact. Not only the composition, but also the physical properties. I mentioned the microfibrillar angle, for example. Okay?
Any
Sir, which process is best for cellulose extraction? Acidic treatment or alkali treatment? Which process is best for cellulose extraction? Acidic treatment or alkali treatment?
What extraction? You mean for the rating process?
Ah, yes, sir.
Uh,
For cellulose extraction.
How we can separate? Yes, it can be an alkali treatment that remove at least part of this material. And then to remove the residual lignin, we can use a bleaching treatment. This treatment, so I don't know very well, but they are classically used in the pulp and paper industry. Because, so in some, otherwise, it's possible, I didn't mention, didn't not highlight this in the table, but some source of cellulose are very rich in cellulose, meaning that there is almost no lignin, no hemicellulose. This is the case, for example, for cotton. Cotton is almost pure cellulose. But for other sources, if you want to extract cellulose, of course, it's necessary to have this alkaline treatment followed by a bleaching treatment, which are the two treatments which are generally used.
So can we use acidic treatment?
Acidic treatments, yeah, yes, it's used also. Yes. It's used. I don't know what it can remove, if there is lignin or hemicellulose. I say I don't know, but we will see that it is used to decrease the size of cellulose fibers. With an acidic treatment, we can degrade, partly at least, the cellulose fibers to decrease the dimension of natural fibers.
Thank you, sir.
Yeah.
Professor, I exactly have the same question what you already answered. The major cases we see it was base treatment, alkali treatment.
Yeah.
So is it because of cellulose means it's a lot of acetal linkage. Inside the molecule you have a acetal linkage and acetals are acid labile. So is it because of when we put acid, acetal linkage breakdown, as you pointed out, cellulose can break down, the fibers can make shorter.
Yes, probably. As I mentioned several times, I'm not chemist.
Yeah.
Also, I came later in the field of cellulose, or later,
Yeah.
not so much,
Yeah.
but well after the PhD. I have to say, I don't know exactly.
So thank you, Professor, for the nice talk. So I have one question in the slide number 36.
36? 36. Yes.
So you explain different patterns.
Yes.
So there in that there is a certain kind of a non-periodic structures, right?
Yes. You mean for the copolymers?
Yeah,
Yeah.
one. The third one, right? Yes. Third structure.
Yes.
The random.
Random. This one.
Yes. So how the property of that device structure will be different from?
From the other copolymers? Or
Yes.
in fact, an important property, but which is not very important for compatibilization, is that this kind of copolymer or this kind of copolymer can crystallize. This one cannot.
Okay.
Because one of the conditions for a polymer to crystallize is to have a regular structure along the macromolecule that we don't have here. We have this regular arrangement here. We have this regular arrangement here, so meaning that these two copolymers can crystallize, maybe not. Some other parameters can be involved, but for sure a random copolymer will be always totally amorphous. But this is not the objective for compatibilizing. In this case, we use a random copolymer with only few percent malic anhydride unite, just to punctually graft this macromolecule on the surface of the fiber. And most of the copolymer is made, for example, from polypropylene in order to interact with polypropylene chain from the matrix. But we'll see later also that this block copolymer can also be used.
Okay. So how do you simulate this kind of a study? So what kind of a softwares you will be using for studying this kind of a response?
Sorry, what?
So do you use any kind of a softwares to study this kind of a structure?
You mean for the block copolymer?
Yeah.
For the block copolymer, so to have this compatibilizing effect, it's necessary to have an hydrophilic block that can interact with OH group from the surface of the fibers. And the second block is generally the polymer that is used as a matrix.
So I am asking, yes. Yes.
Yes.
Yes, sir. Yes. Or you are directly using the,
Which other strategy? You mean when using isocyanate and silate? No. A molecular simulation?
yeah.
Yes.
Yes. Such a
What do you mean by the other strategies?
DFT, different kind of a new,
Yes. I have no experience in modeling, but I think we can model because we have different interaction
okay.
with the OH groups.
Okay, so this is basically a 1D patterns, right? One-dimensional pattern. So in a, okay. 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 Thank you. Thank you for.
Professor, you have any other reagent? As he pointed out, this way you can make a one-dimensional structure. You have any reagent which can make a three-dimensional structure?
What do you mean by one?
Like if you use isocyanide, it has only two arms. So it
Yes.
will grow on both the directions, X and
You mean to
yeah,
have a molecule which is graphed
yeah,
on the cellulose, on the fiber,
Yeah.
with different.
yes, yes.
Probably there are some molecules which are because there are many different options for compatibilization. These are the most used, but there are many other.
Thank you.
So this is a general question. I'm not sure whether it will come in the coming sections or not. Here the talk is basically emphasized on the fiber, actually, sorry, yeah, fiber reinforced biocomposites, right, sir? So once it is coming to a particle reinforced biocomposite, or say a plant extract or a molecule reinforced biocomposite, how the mechanical properties can change, or how can we make it more durable, or yeah, how to change the properties of those things?
Between a fiber reinforced composite and a particulate reinforced composite?
Yes, sir,
Okay.
exactly.
One important parameter that I will mention it later is the aspect ratio of the fiber. The aspect ratio is the ratio of the length divided by the diameter. This is important. To have an efficient reinforcing effect, it's necessary to have an aspect ratio which is higher than a critical value. When considering particulate or fillers, which is called fillers, which can be more or less spherical particles, it can be platelet-like particles, this aspect ratio is very low, meaning that we can only expect a low reinforcing effect. But as I mentioned, when using a filler, the objective is not the mechanical properties. The objective is to decrease the price of the material. So it means that it's necessary to use a filler which has a lower cost than the polymeric matrix. And to keep, of course, some properties which are necessary for the application. So some example of fillers are calcium carbonate. It can be, let's say, paper. It can be the shell of eggs, and so on, some very low cost materials.
So will there be a difference in the cross-linking of the polymeric part and the process that which you have mentioned now using the calcium carbide or paper?
I'm sorry, I don't understand the question.
Sir, while we are focusing onto a cross-linking part of the polymer matrix,
Yes.
and
When
will there be
using
a
a
change?
thermoset,
Sorry, sir?
when using a thermoset polymer,
Yes, sir.
if it is crossing, yes.
Then will there be a change? Will there be a property change with using that cross-linked polymer with the normal polymer part?
Of course. You mean when comparing a thermoplastic and a thermoset polymer? Is this a question?
Yes, yes.
Yes, of course, we have different properties. Different properties and different processing technique. We'll see this just in the next lecture.
Thank you, sir.
Any more questions?
So, since we are dealing with biocomposite, it is equally important to consider both the reinforcement as well as matrix. How can we change the property of a matrix by any cleaner method?
Changing the properties of a matrix by
Any cleaner method?
to have a greener material. Yes, we can change the property using a biopolymer, for example. You have a greener material at the end.
I mean not using any organic solvents.
Ah, yes, you mean making the chemical modification using green conditions. Yes, green chemistry, in fact. Yes, this is a tendency. More and more people try to propose new modification process that can be done in water or in solvents which are not so harmful. The problem with water is that, of course, if you want to have molecules that react with OH groups from cellulose or from natural fibers, if you use water as a liquid, it can interact also with water. But of course, green chemistry is definitively a good solution, because if you use natural fibers and you use solvents or chemical conditions which are not green at all, so the interest in using natural materials is not really important in this case. So it means that the whole process needs to be green to have green materials, of course. But the problem is that, so this is for the chemical modification, but for it's also possible to use biopolymers. There are different biopolymers. Some of them can be biodegradable, but the problem is that most of the biopolymers have poor mechanical properties. I can give you an example that I give always to my students. You can consider, I think it still exists in India, but no more in France or in Europe in general, I think. You know, in the supermarket, you can have bags which can be made from polypropylene or from polyethylene. Okay? These bags are very light. So I think it's typically 9 grams. And in these 9 grams of packaging, you can transport up to 20 kilograms of food or other product. We cannot find any biopolymers that has the same properties. It's impossible, at least for the moment. Meaning that, of course, the use of biopolymer can be important, but for me, recycling is probably more important, because we can keep the same properties, and so we reuse the material. But yes, of course, green chemistry is important.